you to an open source project that we've been working on, and with the latest developments we have decided to fully open source this technology, including electronics board, software that we can, and also the plastic design that we created. What is the application? The application is basically Project Senstar's indoor air quality sensing, and it's basically the hardware looks something like this. We haven't done the plastic CNC work from the company that we got the design, but the electronic boards are printed, and you can also get them made as well. We are using open source BeagleBone, and we are using the open source Project Senstar. And what it does is we are integrating to an indoor air quality sensor from Cubic, and we basically merged everything together with a lighting panel. So here's the software part. We basically have the Linux layer on the left hand side. We are basically reading the UART protocol within the indoor air quality sensor. We're passing the data to Senstar's engine. Then we pass the data to Haystack, and it can be served to SkySpark layer that's built in, which you can buy from multiple areas within the community, or you can send the Haystack data to your cloud. There's also an application called Sedona Framework. The Sedona Framework in this case is used to turn lights on or off, and I will do a demo of that. If you opt to choose utilizing SkySpark, you can basically trend the data and write analytics rules, and you can cluster all these devices within the Fort layer, and you can write X queries to basically look for temperature readings or humidity readings or particulate matter readings for a floor or a location. If you have multiple locations, you can aggregate all of those within a cloud environment. Then you can go back to the Senstar layer and you can ask questions to the cluster to change the colors of the LED. So if you would think of like if the temperatures and humidity is within the range within the floor, you can have a different light turn on. This is pretty much how it works. Let's talk about which parts are completely open source, which parts are open source, but you still have costs to manufacture them. We are using BeagleBone with a hat, so you can basically, it is open source, but you can buy these hardware and different models of the hardware as well. We do have indoor air quality microcontroller maker's board. That is basically, we purchase it from China. There's a paid, the paid application is basically the analytics engine, but you can choose to build your own cloud instance and write back to these devices really easily with an open source project called Project Haystack. Within the application, we are utilizing UART protocol turning into the Senstar engine, and then we write with the Sedona framework, we turn the lighting panel. Again, lighting panel is completely open source, but there's a cost to build them. If you choose to use SkySpark, you can cluster all these devices, you can do pattern analytics and write back to the lighting panel as well. So the analytics is basically, it will look something like this. You can see the temperature reading, percentage of humidity over a certain time. So I can just show you the application right now on how it looks. So this board that you see right here has been working inside my office for a while now, and we were working on the industrial design plastic molding. and we decided to open source everything, seeing the urgency of how humidity, particulate matter really affects the COVID virus infection rates. So this is basically the month of February. You can see the month of January and so forth. So it is actually working very well. If you actually come down to February and March, I live in Austin, Texas, and we do have a lot of pollens. And starting from March 15th, I do see it, the numbers spike up a lot for the particulate matter numbers. You can also see this ppm levels. I turned it off for the last couple of days to set up this environment to show you the technology. So if you want to look at what you will be getting a plastic design for the interior piece. This basically holds up the lighting panel like this, where you can mount it onto this internal plastic model. We are using an existing system that is available out there, existing industrial design called ZN45 from a company, and that company is listed. We have given the design for the hat that goes on a BeagleBone, and also the LED board is completely open sourced. The connection that goes from here to the AM4100L is something like this. It's a JST cable that you would be purchasing. Also, the cable for LED light is basically a box model type. It's basically a ribbon cable that you will have to purchase. The sensor looks something like this. This is AM4100, and it's basically a dev board with CO2 sensor, the particulate matter, temperature and humidity, and VOC is all built in, and it communicates over a UART. Within this area, this board was all together, and we had heat exchange from the LED panel. So within here, what we have done is we have a separator in between, and you can basically completely close it off within that other board that we have designed, where it needs to be CNC'd. I will also post the costs of building those as well. But the application, you install it on a BeagleBone. You can get a BeagleBone like this. This one is from SandCloud, and this is industrial spec. You can also get regular spec within this environment. We don't have a lot of high temperature environments. And the cool part of it is that once you have this, you can cluster all of this together and utilize it from the basically you can control all the lights. Now what I will demonstrate now is how the SandStar sides works and what the concept of it is. So the SandStar side is works in this order. With it, we have a device template, and device template is already mapped to for the CO2 to UART protocol. So you can see in for we are reading out to for the shift registers for the turning the lights on or off. We have the temperature reading mapped as well for the UART protocol. So you can see everything is mapped here, and we have a this is the hardware abstraction layer. We have a software abstraction layer. This is a Zinc grid. It's basically based on Haystack. So if you look at this record editor, it's a tool that we have made so that we can create these tables. If I go to like CO2, you can see that it is channel 58, and we have the tag row CO2, and we have row CO2 marker on it. This is pretty much how we are mapping the software layer on it. If we go to a CC controls as a contemporary controls as a Sedona editor, we can also look at the code in there as well. Inside SkySpark or any other application in cloud, you can actually integrate this to Haystack. So we are reading the data from the system for CO2, for humidity, for particulate matter, for temperature through the Haystack model. So you can see that the PM 2.5 is really high right now in here. Other than this, what you can do with this is that you can see the humidity levels and you can trend it as you saw earlier. If you want to look at the code in the Sedona layer, we have the readings for raw PM 2.5, raw VOC. This is like the raw data. We are passing it to a filter for high and low resets, and then we pass it out to be read by the Haystack layer. We have the tags air, CO2 zone, so on and so forth. So this is basically the virtual channel. We are creating the AV value. In here we have the defined humidity indicator. We can actually import this as a Haystack into SkySpark or to your cloud, and this is basically based on nav name. We are just doing a query to it, and I can actually turn lights on or off, and you can see that that LED light just turned on based on the tag that I had. We can actually cluster all of these devices together and do historical data calls for a floor and say if particulate matter averages for floor A is more than 90, you can actually turn a light on all the devices within that floor. This is a feature that is pretty much built in if you get the whole stack. And you can get those points from anywhere. We are doing this so that facilities can measure humidity and temperature and particulate matter within their spaces a lot easier than what we can do today. And you can get it manufactured anywhere. You can build it on your own. We can try to lower the cost of getting it done. Thank you so much for listening.